And we are back. It is Monday morning, February 8th, chapter 19 coming up. We're moving into the second section, you could say, of the semester. Homework 4 will be due Wednesday, so you can already tell chapter 19 won't be much. It'll just be mainly descriptive stuff, review of acid-base chemistry, and a little bit on applications. But the introduction is important, I think, to review acid-base principles, which can be kind of tricky, right? We got the pKa value, and we have the pH scale. And we'll talk about the ionizing potential of these materials, carboxylic acids. Test 1, last day today over in the testing center, closes at 7. This is when they actually close. The last tests are handed out, what, at 6, right? So don't wait until late in the afternoon. Well, you can wait until 5:30 or so, but make sure you get in there. The test is designed to take about an hour, hour and a half. Shouldn't be any longer than that, but be aware of that. And I think the late fee starts to kick in at 2 this afternoon. Is that right? So sorry about that. But yeah, and then we'll be grading tomorrow. So don't worry about the test until then. When we get the grading done, the scores posted on Learning Suite, and then the exams handed back in the handback slots, which are right out here in the hallway by the west door heading out the building. You'll see my name and then all the slots underneath. We'll hand back then. When you go to get your test, hopefully we don't have a traffic jam there. Try to stay distance, and when you grab your exam, move out of the area quickly. Nothing will be posted there. The key will be posted on Learning Suite, so you don't need to hang out there and try to check your scores. But yeah, just get it, and hopefully we don't. If you see your score on Learning Suite, it's probably back in the slots, so you can come get it any time after that point. So you don't have to count on getting it right after class or whatever. Anyway, questions on anything there? Okay, let's go to the outline first up here. Nick's filming today. Yeah, let's look at the chapter outline here. Carboxylic acids, we've already seen these functional groups, of course, acetic acid being the typical one. We've learned these functional groups a while ago. We've learned a little bit about, the properties and even the spectroscopy, the NMR and the IR of these things. We'll review that a little bit, but there'll be some new common names we'll have to talk about. We'll do the naming through 10-carbon carboxylic acids, so everything from formic acid up to decanoic acid. We'll review the common ones, benzoic acid, and we'll do the diacids too, oxalic acid through pimelic acid. Examples, and these are very versatile, right? They're all over the place in nature. As metabolites, you've probably heard of lactic acid or gamma butyric acid, amino acids, of course, the building blocks of proteins, and drugs, aspirins and prostaglandins, which are the naturally occurring hormones in the body that control inflammation. We'll see how these drugs, aspirin, affect prostaglandins. You'll need to know a little bit about that, but again, it relates to the functional group and what we're talking about there. So a little bit preparation. We'll review some of these. You already know a lot of ways to make carboxylic acids, believe it or not. The reactivity, that's the key thing. We'll start out with that on the board here in a second. They can ionize. So it's one of the few functional groups that, depending on the pH, when you put them in water, depending on what that pH is, super acidic, carboxylic acids will stay protonated. They'll be neutral. But if you go higher into the basic range, beyond the pKa value of a carboxylic acid, you can ionize it, and you mainly have the salt form. And that's kind of unique among functional groups. We'll see the amines also can either be ammonium cation or neutral amine, depending on the pH of the solution. Now, that's kind of a review. I hit that topic pretty hard in 351. Some people are nodding their heads or looking like, oh no, not again. But that's okay. We'll review that. It's an important topic to get into reactivity, and we'll relate the pKa's of other hydroxy acids, including alcohols, which also have an OH group, just like the carboxylic acids. But we'll get into that. We'll do extractions. We'll use that ionization to do some simple separations. We'll talk about biological ones sulfonic acids and phosphoric acids, and then amino acids. A little bit on that. We have chapters coming up later on the biomolecules, of course, and amino acids will feature prominently there, making proteins, and we'll say a lot more about amino acids in general. So we just have kind of an introductory thing here on them. Okay, Hall of Fame, yeah, okay, a lot of different carboxylic acids. Pick your favorite one. Don't memorize these, but know, why these are acids, right? Acetic acid, there you go, simplest one. Aspirin's also a carboxylic acid, right? It's got benzoic acid in it, and it has an extra ester here. Tartaric acid, glutamate, that's one of the 20 amino acids that make a protein. It's also a neurotransmitter. This is the excitatory neurotransmitter in the body. That's an important one. The tryptophan, the precursor to serotonin, the feel-good hormone. Citrate, pyruvate, these are metabolites involved in glycolysis in the citric acid cycle. Niacin, one of the cofactors. Cipro, floxacin. This is one of these newer generation antibiotics. NutraSweet, you know what that is, right? Artificial sweetener. Here's one of the prostaglandins. You see the carboxylic acid here. The fatty acid chain, the cyclopentane, that's typical of the prostaglandins. All those hormones have that, controlling inflammation and pain. So those pathways are very important in medicine and in the clinic. So knowing a little bit about prostaglandins is important there. Oleic acid is a fatty acid. Ascorbic acid, of course, vitamin C, the water-soluble one. And that one, do you see a carboxylic acid there? Not really. But this OH group here is conjugated through to the carbonyl. We call that a vinylogous carboxylic acid. We can deprotonate this one right here and get that same resonance stabilization. So going back to the structure will be an important thing. Hall of Shame also, I'm not going to spend a lot of time here. Some of these just smell bad. Some of them have the toxicity. Some are drugs, right? LSD, trans fat in the diet that's been removed, fortunately. Yeah, let's not say much there. Oh, butyric acid form. We'll get into that a little bit. Okay, let's go over to the board here and get into reactivity. And the first thing I like to point out about carboxylic acids is they're a member here of a broad class of carboxylic acid derivatives, we say. So everything from an acid chloride, which we talked about for Friedel-Crafts acylation, right? Very reactive for Friedel-Crafts. It's got the chloride on there, very good leaving group, okay? In biology, we also have these acyl phosphates. This is a form of an anhydride, actually, okay? We saw the other anhydride before, which was acetic anhydride. If we dimerize two carboxylic acids, we get an anhydride. Well, that's just kind of a leaving group on the side of an acyl. And same thing here with the phosphate, okay? These are also very reactive. So we've got something about hierarchy of reactivity here. Now, this will actually be a later chapter. We'll do derivatives of carboxylic acids and a lot of these other functional groups. I like to point it out up front how it relates to carboxylic acids. It's just something else taking the place of the OH group on the side of the acyl, okay? We can make a lot of these derivatives, but this hierarchy of reactivity has to do with how good of a leaving group is on the side here, right? Chloride's very good. Phosphate and acetate are good. Sulfide is also pretty good. In fact, there's a lot of acyl sulfides in biology. A couple of you guys have gone on to biochem and some other classes and seen these type of guys that are used in the construction of different things, including acyl triglycerides and some other functional groups in metabolism there. But that's a thiol ester or sulfur ester. And then the oxygen esters, they're comparable in reactivity to simple carboxylic acids. And you look at that, what leaving group would that be? Well, O minus, right? Either hydroxide or OR if it's an alkyl group. So you already kind of have a feel for why these are important. They're very versatile. Amides here are very stable, okay? That's because that amine coming off with a negative charge would be a very poor leaving group. So would O2 minus coming off as a leaving group, okay? So the salts, the carboxylate salts of carboxylic acids, bad leaving groups, okay? Now, reactivity. Don't worry about this yet. Just be aware of it right now. Here's where we begin to talk about reactivity, right? acid-base chemistry. And this should be a review, hopefully. Go back and look at previous chapter in 351. I can't remember offhand. I think it's chapter 4 or 5, I think, or acid-base chemistry in general. Or back to your Gen Chem topics. So hopefully you've seen these before. But I'll review enough here, I think. So let's put acetic acid in water. To what extent will it form its what? Conjugate base and the conjugate acid. I'm not drawing those terms out. You should be aware of those terms. Carboxylic acids are Bronsted-Lowry acids. That is, they can donate a proton, okay? Here's the proton it's going to donate. Not these three, okay? But this one right here. How does it do it? Well, we can push electrons, right? Let's leave the electrons behind on the conjugate base and form hydronium ion, okay? Well, that looks fine, except I've drawn this as what? Equilibrium. Which side does this lie on? To the left? Does this favor starting material, or does it favor products? Should we poll the class and see what we get here? Who says this favors starting materials? A couple people kind of hesitant there. How many people say this favors products? Oh, a couple more. Okay, how do we figure this out? Well, we have the equilibrium constant K, and we can draw an equilibrium constant for any reaction, right? Ka is a special one concerning Bronsted acids. And this is the concentration of the products, which will be acetate. And what do the brackets mean? Molarity, right? Times hydronium ion over what? The concentration of the starting material, which is acetic acid. Notice I left out water. Why did I leave out water? This is under dilute conditions where the concentration of water stays constant, 55 molar, whatever it is. So that's the definition of a Ka expression. It's the ability of this to donate a proton to that, right? Ka for water. What is this? This can be measured. It's 10 to the minus 5. Is that a large number? No, that's super small, right? Which means what? Let's poll the class again. Who says starting materials are favored? Still kind of hesitant. Look at the expression here. What does this mean? Concentration of this is going to be what? A lot larger than that, right? Okay, simple math, right? All right, let's point it out again. Who says starting materials are favored? Yeah, almost everybody, right? This is a super small number. So what do we say? Acetic acid is a very weak acid. Okay. It only ionizes to that extent, 10 to the minus 5. Okay. This is a logarithmic scale. It's kind of a pain. So we have another value here. Definitions, right? What's this definition here? pKa equals minus log, these are log 10 values of the Ka. Okay. That minus means this is going to be an inverse scale now. So what's the log of 10 to the minus 5? It's minus 5. Then we take the minus of it. So what's the pKa of acetic acid? It's equal to 5. That's the number you should have memorized. It's kind of in the middle of the pH scale, right? Okay. It's a little bit on the acidic side. We'll have to review the pH scale. But there you go, definition-wise. Any questions on that? Hopefully this rings some bells. If not, review this stuff. Let's compare this to this guy. HCl. Same thing, water. Equilibrium, your conjugate base is chloride. Same thing here, hydronium, right? If we donate a proton to water, there we go. All right, let's pull the class. Who says this favors starting materials? Who says this favors products? Yeah, okay. And why? This is super strong, right? Acid. The pKa of this is minus 7. And the pKa of this is minus 2. Now, when we know 2 pKa like this, we can figure things out, right? Here, we said, okay, this is not favored. So what? This is a stronger acid, pKa of minus 2, compared to this, which is a pKa of 5. So we always use the stronger acid and go in the direction of the weaker acid, right? Okay. So acetic acid can't fully protonate water. It can to some extent. You put acetic acid in water, it will get acidic. but it won't drop all the way down to this, okay? Here, this is complete. And let's do something a little different here. So again, this is strongly favoring that because we're using the stronger acid going to the weaker one. Let's define another thing here, the K of the reaction, which is equal to 10 to the pKa on the right minus the pKa on the left. So this is how organic chemists think about equilibrium with acids. Let's see, 10 to the pKa on the right minus 2 minus 7. What does that come out to be? 10 to the 5th. That's a huge number, right? Which means what? This equilibrium is favored, okay? And there's some other things we can point out here. If this is a super strong acid, its conjugate base is super, what? Weak, okay? So we're going to point some of those relationships out. Okay, how are we doing so far? The review's not too bad, is it? You follow this stuff? Weak acid versus strong acid, pKa value. Okay, let's use this now. Okay, we've defined some things, we've compared it. Now let's use this. Let's do acetic acid again. Stronger base, sodium hydroxide. Equilibrium again to acetate. That's the abbreviation for acetic acid conjugate base, acetate, ACO minus, okay? And then what's our conjugate acid here? Oh, it's water. A little bit different. We're using hydroxide. This is a salt material, white salt. We can weigh that out, dump it into an amount of acetic acid. What are we going to do? Okay, let's think about the reaction here. What's our reaction equilibrium, or K for our reaction, right? Let's just define that again. And we need to have the pK values again. 5 for the carboxylic acid. What's the pK of water? This is -2. That's for hydronium ion. What's the pK of water? Anybody remember it? It's a good one to know. 15.7, 15 or 16. Let's just say 15. Okay. pK for the reaction, what's this going to be? 10 to the 1 on the right minus the 1 on the left. Is this a favored reaction? Everybody see this has to be completely going to the right there. So this is a strong enough base, of course, and you know hydroxide is a strong base. But to what extent would be that? Oh, it's complete, right? It's going to go all the way to this. Okay. So will this one with hydrochloric acid donating to water, it'll go to hydronium ion completely. So if you put 1 mole, let's go back to this one just for a second. If you put 1 mole of acetic acid, hydrochloric acid into water, then the concentration of this changes to the concentration of this, right? And it's 1 molar, okay? Another definition here, what pH is equal minus log of the concentration of hydronium ion, right? And I'm running out of room here. So put this in, a strong acid completely ionizes, completely donates to water. If you put in 1 mole per liter here, you get 1 molar hydronium ion. And then what's the log of 1 here? The pH will be 0, okay? And that's the superacidic end of the pH range. It goes from 0 to 14. We'll review that. We'll review pH, okay? Same thing with hydroxide. If we put that in water, we have 1 mole of hydroxide then, which is 10 to the minus 14 hydronium ion. And that's a pH of what? 14. We'll have to review that. We'll review the pH skills. But right now, I just want you to appreciate this reaction using the pKa's here, and we're going what? Toward the weaker acid. It's an inverse scale, so the larger the pKa, okay, the weaker the acid, okay? Okay, if it's a small pKa, and here we cite HCl, right? pKa of -7. super strong. Okay, so it's an inverse scale. Just got to get used to that. All right, let's try one here as a class. Let's take acetic acid again, plus ammonia now, and go to acetate. And ammonium will be our conjugate acid. Now, these are different things. Neutral ammonia, okay, versus ammonium. Ammonia is the base. Ammonium is the acid, okay, the conjugate acid. That's good. Where's this equilibrium lie? Should we pull the class? Who says starting materials are favored? Who says products are favored? Oh, okay, phew. Now, how do you know that? We need to know something else here, right? pKa 5, acetic acid. pKa of what here? 9, right? That's another one you should memorize. And that'll be the point in the pH scale upon which, if things are more acidic than 9 pH, will be protonated. It'll be ammonium. If we're on the higher side of this on the pH scale, the more basic side, remember the pH scale is also an inverse scale. The lower the number 0 is actually where your hydronium ion, right? Acid is at its highest concentration. If you're way up here, 10, 14, whatever, you have minimal acid, a tiny amount, trace amount, and more hydroxide, right? Okay, so if we're on the basic side of that, we can begin to deprotonate that and have ammonia in there. But what's our reaction here? Let's do our K for our reaction. It'll be 10 to the 9 minus 5. So yeah, this will also be favored, right? 10 to the 4th by a part per thousand, okay? So you get a feel for how we're going to use these things. We need to talk about, acid-base strength and why different factors affect that, but we'll get into that. Let's do nomenclature now. There's no questions on this. So yeah, is it helpful to review these 4 things here definition-wise, comparing to a strong acid, using it here with hydroxide as base, and then comparing it to another functional group, which will be amines, okay, an ammonium. All right, let's get into some naming here. The naming of a carboxylic acid is alkanoic acid. Alkanoic acid, where the alkane part is the original parent, and that parent includes the carbon of the carbonyl, okay? So we can draw this, which would be a 1 carbon acid, and we count that 1 carbon. What's the 1 carbon parent hydrocarbon? Methane. So this would be called methanoic acid. No chemist calls it that. It has a common name, formic acid. Okay. Comes from ants, formiga, the Latin term for ants. Red ants excrete that stuff. That's an irritant. Okay, how about this one? Ethanoic acid. We've been talking about ethanoic acid. I haven't been calling it that though, right? What do we call this? What's the common name? Acetic acid. Okay. Okay. And those are the 2 common terms that we see all the time. How about this one? And now we get into the more systematic naming. 1, 2, 3. This is propane. So it's propanoic acid. Sorry, I'm not going to keep writing acid there. Okay, how about this one? Butanoic acid. Okay, propanoic acid and butanoic acid are produced by bacteria on the skin, and they tend to be very pungent. In fact, the essence of body odor is butyric acid, okay, butanoic acid. And there I used another common name, butyric. That's another common name, butanoic acid. Both of these are accepted by the IUPAC, but this one is kind of an archaic term. Propionic acid is the one that's common for propanoic acid. On a quiz or a test, just use the systematic IUPAC name and you'll be fine. but I'll just mention some of the other ones. Valeric acid is the common name for this. Pentanoic acid. And here I like to point out the numbering because we got a long enough chain here. This is the numbering system. If you've got other things on there, you can name those as prefix names. The parent is pentanoic acid now. We also have these common, so notice number 1 is actually the carbonyl. So you can't have really any other substituent at the 1 position. Everything is 2 on down relative to that, okay? And then we also have these common position names, alpha, beta, gamma, delta, okay? And those are position markers that we use when we talk about mechanisms sometimes. This is the alpha position to that carbonyl. This is the beta position. You'll hear those terms as well. Anyway, a little bit on the numbering. Let's see, hexanoic acid. And I'm not going to keep going up, but we could do heptanoic, octanoic, nonanoic, decanoic acid, and we'll stop there. Okay, we'll just go up to 10. Well, what would be hexanoic acid? Well, it'd be 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Okay, and I think you can see that. Make sure you count that as part of the name. 1, 2, 3, 4, 5, 6. Yeah, that's good. How about one where we combine a couple things? So what would we call this? Well, it's propanoic acid, but look, it has an alkene in it. So we call this 2-propene. Okay, that's what the 2 refers to, propenoic acid. So you see we can accommodate other functional groups. The carboxylic acid gets priority. It's always numero uno, okay, by definition there, okay. Anyway, that gives you a little bit of naming there. Let's do fatty acids and diacids. Okay. So far so good. That fits nicely into the IUPAC rules, I think. A couple other common names here. What's that one? That's that's octadecanoic acid. It's a C18 acid. Count up all the carbons. Make sure I got 18 in there. Do I have 18? You could call that octadecanoic acid. It's also called stearic acid. From what? From steers, from beef tallow. Okay, that's where the term comes from. It's an all saturated, we say. There's no double bonds in here. It's a fatty acid. Okay. Those are very important in biology. We have the hydrophobic domain, the hydrocarbon part, and the hydrophilic, the ionizable part. We can form the salt of stearic acid. And then we have the common unsaturated one here. At the 9 position, we have a cis double bond. That's also C18, but at 1, 2, 3, 4, 5, 6, 7, 8, 9, we have a cis double bond. Okay, this is the bullfighting fatty acid. Anybody know the name of this one? What does the crowd yell when the bullfighter makes the bull go under the cape? What do they yell? And also at soccer games. Olay. Okay, this is oleic acid. It's also the main constituent in olive oil. It's a monounsaturated, okay? Unsaturated. You've got 2 hydrogens removed there, and they're almost always cis, okay? You saw the trans one on the, so it's the fatty acids. Common cyclic ones, we're not gonna get into this. There's a lot of variations of these. How would you name that? The parent is cyclohexane, and that's how these are named. Cyclohexane is the part of the prefix name, and then just carboxylic acid. Cyclohexane, carboxylic acid. So you could have cyclopentane or cyclobutane carboxylic acid. Yeah, so the naming there is a little bit different. And you already know this one. What's that? Starts with a B and it has that oic acid name on it. This is benzoic, right? Okay, question on any of these names? All right, let's do the diacids. Diacids are important for biology and for metabolism. And I'm always amazed at how these names come up periodically. It's a lot of new names, so these diacids are a little bit tricky this way. But if you have both ends of a chain with carboxylic acids, and this is the simplest one, right? Two carboxylic acids on the end of ethane, you could say. In fact, you could name this as ethane dicarboxylic acid. The IUPAC accepts that. But that's not what you'll see in biology and biochem or other metabolism classes. This is what? This is oxalic acid. The oxalic is accepted by the IUPAC, and it's a 2-carbon dicarboxylic acid, oxalic acid. Maybe you've heard of calcium oxalate, which is a calcium salt of oxalic acid. Anybody know what that is in the clinic? Calcium oxalate. It's not very soluble in water, I'll tell you. It forms a salt in the body. It can cause a lot of pain. And if it's a bad problem, what is it? It's, anybody know what calcium oxalate is? Kidney stones. Okay, if those build up, you got a problem. So we need to talk about solubility here in a little bit. But there's one for you, calcium oxalate of that. And then we have this one, malonic acid. And I'm leaving off the A there. Malonic acid is the 2-carbon one. And then we've got succinic, which is 4. And then we got the 5 one, which is glutaric. That's related to glutamic acid, which is one of those amino acids. It has an amino group here. That'd be glutamic acid. This is glutaric acid, if it's just the 5-carbon dicarboxylic acid. And then we've got adipic, sorry, a couple more. Adipic. It's in apples. And then we got pimelic, which is also in fruits. And how many is that? That's 1, 2, 3, 4, 5, 6, 7. So we went from 2 to 7 here. Oxalic, malonic, succinic, glutaric, adipic, pimelic. Okay, I'll teach you a mnemonic device to remember these, and you'll never forget these. And you'll thank me later on in biochem that you already got these down. Especially succinic, glutaric, these, oh, and malonic also. You see these all over the place, actually. So let's go with, oh my, such good apple pie. How's that? In fact, these last two are in apples, actually. Oh my, such good apple pie. Now you'll always remember the 2 through 7 dicarboxylic acid, oxalic, malonic, succinic, glutaric. And you can have other substituents there. You can have, chloromalonic acid. You can, have two things here, 2,2-dichlorosuccinic acid. So I think you can see how that opens up a lot of other naming there. Questions on that? Do you like my mnemonic device? Oh my, such good apple pie. Okay, maybe. I don't know. If you don't like pie, maybe you don't like that. But all right, preparation. Actually, you already know a lot of ways to prepare carboxylic acids. And I like to abbreviate these, or at least review them a little bit, because, reactivity is important. So preparation, carboxylic acids. And this is probably the most important one, primary alcohols. can get oxidized, and it has to be on the end. Carboxylic acid has to be on the end, right? So if we can oxidize that, and this is an oxidation, right? We've added oxygen, taken off hydrogen. What's our reagent? We know that from 351, right? What is it? Chromic acid. The same thing that does that alkane benzene oxidation to benzoic acid, right? And there it is, carboxylic acid. It stops at that point. It's got to be primary alcohol in order to go all the way to carboxylic acid, right? So other combinations you can use there, the chromium salt and then sulfuric acid. So you don't have to have the chromic acid directly used. You can form it in the flask and then dump in your primary alcohol and get that. Let's review this aromatic thing. So any type of hydrocarbon, it can't be a tertiary alkyl group. We get no reaction. You can use the same thing, chromic acid, or what? Potassium permanganate. There's a little bit of review that might help you on test one here. So it's a good thing you came to class today or watched the video ahead of taking test one. But this will form what? Benzoic acid. And here I'm abbreviating things a little bit more. Little p, little h means phenyl. So it's a phenyl group with a carboxylic acid. This is benzoic acid. Okay, I'm just abbreviating it. So get used to some of the abbreviations that you'll see there. There is one more that we did a while ago. Ozone, O3. Remember ozone with alkenes went to ketones and aldehydes, depending on what was on the alkene. But now with an alkyne, if you do ozonolysis here, and you have to work it up, you know, water has to get involved. The mechanism's a little bit complicated, but you can get straight to the carboxylic acid. And that's cleaving right here. So whatever, these are two methyls, so you generate two acetic acids there, but if you got other things on your alkyne, that could be different here, okay, for ozonolysis of alkyne. Questions on the prep? I think that should be pretty good. Let's get into reactions beyond just acid-base chemistry. Okay, that's interesting enough, acid-base chemistry, and we'll be doing that, of course, on Wednesday too. But let's review reactions. And some of these are ones we're going to be getting into. You should be okay with this one too. More acid-base chemistry. But here we're reacting acetic acid with a stronger acid, okay? Sulfuric acid. The pKa of sulfuric acid is -7. So we're going to go with that stronger acid. We could draw out the equilibrium definition for this. Well, what would this be? Let's just look at this. We're going to use lone pair here as a base, right? That's okay. We can use weaker acids as bases if we have a stronger acid, okay? Super strong acid. That's one reaction. So using it as a base, okay? How about using it as an electrophile? So yeah, it's a carbonyl. So that carbon there of the carbonyl is partially positive. It's electrophilic, we say. It will react with nucleophiles. So here's a nucleophile we'll see later on. Lithium aluminum hydride, okay? And this will actually be an equivalent of H-. There's 4 of these hydrogen on lithium on the aluminum salt, lithium salt of aluminum tetrahydride. And so we'll actually add these here and do reduction reactions. I'm not going to draw out the product. Eventually this will go to the primary alcohol, okay? We'll have to do that twice. The mechanism will be a little complicated. But there's carboxylic acid acting as what? An electrophile, okay? It's because it's got that partially positive character. And strong enough nucleophiles can add there, okay? How about reacting it as a nucleophile? Can we do that? Well, we got lone pairs here all over the place, right? In fact, we can soup it up even more. Let's react it first with a strong enough base, hydroxide will certainly do it. And let's form acetate. Okay. Now, the general term for this is alcanoate. Okay. And you should put the name of the metal in the front. So this is sodium ethanoate or sodium acetate. Okay. The 8 here takes the place of the IC acid. And here we form the conjugate base of our carboxylic acid. Okay. So yet another naming thing here, alcanoate. Metal alcanoate, we can have sodium benzoate, we can have sodium propanoate, we can have potassium butanoate, or whatever, okay? Now, what? This is a charged nucleophile, right? So what can it do? Well, let's do a reaction with methyl iodide. That's actually, what, a 351 reaction. Charged nucleophile, primary leaving group. What's going to be the product here? Yeah, it's going to be the ester, okay? We'll learn about esters later on. But there, you just made that bond with the leaving group here. You could push the electrons, knock off the iodide, and form the ester. There, we're using the alcanoate as a nucleophile. So you see the versatility of carboxylic acids. There aren't many functional groups like that, where you can do such versatile things and under mild conditions, either form the neutral thing if we keep the solution acidic, or if we make the solution more basic, have it ionized and more nucleophilic. Okay, so that back and forth will be an important thing there. Let's look at some of the properties of these salts and maybe a little bit on solubility. So reactions, now a little bit on properties. And we're going to look at solubility. Solubility in water, right? So, how about sodium acetate? What do you think about that? It's a salt, right? That oxygen, sodium ionic electrostatic bond, right? Going to dominate the molecule. Even though we have covalent bonds also in the molecule, right? The carbonyl and then the carbon hydrogens. It's a mixed molecule, you could say. It's a chameleon. It has covalent bonds and an ionic bond. And that's really going to dominate things. It's infinitely soluble in water then, right? You can organize water around the sodium and around the hydrogen. Now, the corresponding carboxylic acid, this is a liquid in pure form. I need to bring in those bottles. Pure acetic acid in its protonated form. If you put that in water, that's vinegar, a 5% aqueous solution. That's vinegar of the neutral protonated thing here. This is a liquid. It has a boiling point of like 118 degrees. This has a boiling point of over 800 degrees. In fact, this has a melting point around 350 degrees. So this is definitely a salt, okay? Solid material. Very different. This is also, though, infinitely soluble in water. In fact, anything 5 carbons or less, carboxylic acid will be infinitely soluble in water. Why? Because you have, hydrogen bonding with water, right? So this can do a lot of interactions with water and help make it more soluble. But if this gets too big, let's see what happens. How about this one? Here's a longer chain one. Is that decanoic acid? What is it? 1, 2, 3, 4, 5, 6, 10. Yeah, that's decanoic acid. What do you think about its water solubility? Well, it's 0.003 grams per 100 milliliters. It just went way down, didn't it? Why? Because now you have this long fatty acid, this long hydrocarbon chain. So that affects us. You go from infinite solubility at all concentrations down to almost nothing. Okay, what about this one? That's 7 carbons now, right? Benzoic acid. How soluble in water is that going to be? Is it going to be as good as this one? No, certainly a lot less. Going to be as bad as that one? Should be in between, right? Now don't memorize these numbers or anything, just the trend, right? This is 0.2 grams per 100 mils. And these units are kind of weird, I think, for solubility, grams per 100 mils. 100 mils is what, a tenth of a liter. So it's like half a cup, okay, of water. So it's not very much. And that's certainly not very much. If you exceed that concentration, this precipitates out, right? Doesn't stay in solution. All right, well, let's look at the salt form here. Now, are salts infinitely soluble? No, they have a limit, okay? This is infinitely soluble at all proportions. However, salts have this electrostatic interaction, right? And that's kind of counterintuitive, but you remember solubility constants, KSP values in Gen Chem? So there's a limit here. Let's see, sodium acetate is 100 grams in 100 mils. That means if you exceed that amount in 100 mils, and that's a lot, right? 100 grams in a half a cup, that's very concentrated. But if you exceed that, this will begin to precipitate out, okay? Now, this guy, 0.21 grams in 100 mils, the neutral thing. But let's look at sodium benzoate now. I'll draw it out. We can form that with hydroxide, right? What about its solubility? I've got the number here. Is it going to be 100 grams per 100 mil? Is it going to be infinitely soluble? No, it's going to have a limit, right? Is it going to be higher or lower than this 100 grams, do you think? It's going to be lower, but not much. It's 60 grams per 100 mils, which I think is kind of amazing because you got this non-polar thing, right? But what's helping it out here when this is now this, right? So this can organize around water, right? And this ionic thing can really help you out here. And this salt hydration effect makes this much more soluble when it's a salt as opposed to when it's neutral, okay? And that's kind of a key thing comparing those two things, okay? So solubility, depends on polarity here. Of course, carboxylic acids are polar enough. Most of the small ones are infinitely soluble, but yeah, if you have big hydrocarbon chain, it goes down. And then salts themselves do have a limit, okay? And this neutral, and certainly, because it's not the electrostatic thing now, the salt hydration effect's not in there. This is increasing the solubility greatly of the salt compared to the neutral thing, okay? Now, don't memorize those numbers, just the trend. Let's use this now to separate a couple guys. Well, I'll let you think about this maybe. So let's do what's called an extraction. In this extraction, we're going to use the ionizability of carboxylic acids to our favor. We have a mixture of benzyl alcohol and benzoic acid. How can we separate those two? Well, we're going to think about solubility. We're going to think about ionizability. First, we're going to react at a mixture of sodium hydroxide. And we're going to have ether, which is a non-polar organic solvent. And we're going to have water. Okay? Then we're going to put the whole mess into what's called a separatory funnel. Now, if you've had any lab classes, you've seen these funnels before. There's a valve down here. We're going to have our solution here. And the ether is going to be on top. And the water is going to be on the bottom. But you see, we've treated it with sodium hydroxide. So let's see. Sodium hydroxide. Will that be enough to take off that proton too and that one? Let's just put in one amount that has an equivalent that corresponds to the benzoic acid. So you see our benzoic acid will now be what? Benzoate. And that increases the solubility greatly to be in the water, right? And then our nonpolar thing, that's where our benzyl alcohol will be. So mechanically, do you see how we can separate this now? We can just open the valve and let this drain out. And we'll have the aqueous part here, the water layer, as the salt form, right? And then we'll have the ether with the pure alcohol, okay? And yeah, we're out of time. We'll finish this next time. How do we get these two completely separated? Without doing a distillation or crystallization, we're just relying on ionizability, okay? And extracting it, partitioning it between two different solvents. Water, the more polar one, and the nonpolar ether. So I think that's good. That's enough for today. Good luck on the test, and we'll see you on Wednesday. Thank you.